This one is working.
Okay. I think we can already. We'll try. Is this one working? Yeah. Testing, testing. Thank you. Just leave it right here. All right, class, we've got about a minute before technically the class starts. What I wanted to do today, I'm going to answer your questions, but what I wanted to do today is just explain complex power to you again, since we have everybody here. And I want to do it from a perspective of if I was sitting in your seats, what I would want to hear to help me. Now, complex power allows what we're doing now to be done in a simpler way. So you know you're figuring out how much power is actually absorbed, then you're finding out the current and the angle with the current, then you're finding out things like the source voltage. You all with me on this, class? Now, there's on the PowerPoint that I provided, there is information about complex power. But from the comments, at least a couple of comments I got prior, the PowerPoints don't seem to be absolutely clear. So this is the reason I want to take time today to talk about how to calculate it and then why it's so important, okay? All right, so in general, when we talk about complex power, this is the symbol right here, it's S. Right here, S. It's V times I conjugate. Everybody here should have heard of conjugation, but I'm going to take a moment and explain conjugation now. How many have heard of conjugation? Raise your hand or nod or do something. Everybody in this classroom should have had that in your mathematics courses as well as in some of your engineering courses. But let me explain that in general. I'm going to take a moment right here and just do it. This is what conjugation is. And if you can't see, let me know, please. Anything that I'm doing that is not clear, let me know. Can you all hear me, first of all? In the far corners there, guys, and over here. Yeah, you can hear me? And can you all see these screens okay? Okay. If anybody has a problem, let me know. Conjugation is this simply. If you have something and you say that, I'll say V is equal to some magnitude 10 at an angle of 20 degrees. V conjugate, the symbol is an asterisk, is simply same magnitude 10, the angle changes sign, minus 20 degrees. That's as simple as it gets. That's all you do. And you can, instead of having 10 here, put in an arbitrary value V naught. Instead of 20, put in an angle theta. Now, the reason I use real numbers is because it's my personal belief that real numbers make more sense to people. They like real numbers when there's examples. It seems to be clear. I know it's not mathematically rigorous, but it works. Next, if you have something where you talk about conjugation, but it's not with a magnitude and an angle, rather a real value and an imaginary value, here's what happens. If I have V is equal to like 5 plus J7, that's a voltage. And if I wanted to know what V conjugate is, it's simply going to be 5 minus J7. That's it. Now, that's as simple as it gets in terms of understanding it. There's a lot of implications. However, that's all it takes to understand complex power. And that's all you need to know, excuse me, conjugation. Now, complex power, on the other hand, here, are there any questions about conjugation? How many remember it now? All right, if you do not remember this, it's troubling because everybody here should have been exposed to it at least once, preferably 2 or 3 times. All right, if you haven't, now you have. And it's used all the time in engineering. You may have seen instead of a J an I. I is imaginary. We don't use I in electrical engineering because I is indicative of current. That's why we use J. That's the only reason. So getting back to this, this is complex power S. It's V times I conjugate. That voltage and that current are referring to a specific component. Here I'm going to go ahead and draw it. I'm going to just have a component here where I have a plus to minus voltage. That could be with a complex voltage in terms of a magnitude and angle or a real and imaginary part. And I have current entering the positive terminal. Now remember, that current has to enter the positive. It's going into the component in the positive terminal, not coming out, okay? So therefore, the complex power associated with this little drawing here would be this. Complex power has a real power, capital P, and that's what we've been dealing with when we talked about power so far. That was average power. The units of that are watts, plus JQ. Now, Q is called a reactive power. The reactive power does not have the units of watts, technically. They are the same, but they're not the same. They have to be the same if you add them, but to distinguish these two, the power here will be in watts, and I'll put this down again. So this would be in watts. The power here is in something called volt amps, or reactive volt amps, pardon me. It's reactive volt amps. R is just reactive. Now, it will be clear to you in a second, and you're not being tested on this time, but I want to make sure you understand that Q is a reactive power. It is never dissipated. Do y'all remember me talking about capacitors, inductors creating reactive power, or a power that is not dissipated? Any energy / power associated with a reactive component, a capacitor or an inductor, is brought back into the system. It's never dissipated. Follow me on that, class? Resistors dissipate power. They turn it into heat mainly. Now, capacitors and inductors don't. So that's reactive power in a nutshell. So why is reactive power important to us should be the next logical question. Here's 2 reasons. The first, I'm not even going to write down, I'm going to tell you. The sum of all the reactive powers in a system is 0. So the reactive power supplied is equal to the reactive power dissipated in a sense. And therefore, if you have 3 of the 4 reactive powers, you can always find the 4th, because set everything equal to 0 when you add them, and you can find the 4th. Now, this is akin to, if you think about it, to the sum of all the voltages around a closed loop being 0, or all the currents entering a node equaling 0. Whatever goes into comes out of. It's the same principle. And it's really a principle of conservation of energy. In this case, it's conservation of complex power. It's energy per unit time. Are we good on this, class? Now, the second reason, and the most important, most applicable, especially to industrial engineers, for those industrial engineers here, is that complex power allows you to do a calculation for the value of a capacitor so you can lower the complex power of a system. Before I start just scribbling, I want you to hear me. You all realize that you would like the power factor to be 1. In other words, the difference in phase angles to be 0 if you were running some sort of a power plant, because the further off your plant is from having a cosine of 0 or 1 for the power factor, the more money you're going to pay. That's what it comes down to. It's always a cash game. All right, so how do you reduce the angular difference between voltage and current is by adding a capacitor, almost always in parallel. Now, the reason I say that almost always is because there will be a problem that makes sure that you know what you're doing, where they give you something that has instead of having a lagging current, having a leading current. You've had one problem like that already, all right? That is basically fiction. All right, maybe there's something out there that does that. I've never encountered it, and I don't know what it is. But if you understand the concept, when you see something that has a power factor or has a current leading a voltage, you would know that that, in fact, is an odd thing. And then you wouldn't put a capacitor in parallel. You would put an inductor in parallel. In other words, if the system is primarily reactive caused by an inductor, then the element you're going to put in parallel is a capacitor. If it's got a capacitive nature of current's leading voltage, then you're going to put an inductor. And that sort of makes sense. Whatever the system's got the most of, inductive reactance, you want to put in parallel something that's got capacitive to get rid of it. That kind of is intuitive, isn't it, class? Now let me show you this in a nutshell, how you would use it. And for this one, now how many at least understand what I'm getting at when I say complex power? With me? Now I'm going to talk about the complex power associated with a capacitor, okay? Remember, the sum of the complex powers is always going to be supplied is equal to dissipated. And I'll show you more in a second on that. So now, before I go down the route of just going through examples ad nauseum for no reason, let me show you the real reason behind this. Let's take a capacitor. First, let's take, voltage here. Suppose I have a voltage where I have plus to minus, and just call it V here, call it V load at 0 degrees RMS. Now, this is a plus to minus voltage. I can put anything I want between those. And if you want to, you can go ahead and put a supply here of supply voltage. But you've got plus to minus, and you could say this is plus to minus. V, call it V source, which is, in this case, V load. So there is no line losses. Are you with me? I'm just showing you two wires that got a potential difference. Now, if I put a capacitor here, I want you to think about this. If I put a capacitor here, we know the voltage across that capacitor. Do you agree, everyone? Now we need the current through the capacitor. Well, for a capacitor, the capacitive reactance, and I'm going to use the term Z sub C here to indicate the impedance of the capacitor, would be equal to 1 over J omega C. Does everybody agree with that? Right? It's 1 over J omega C. Whatever value J omega C is, so be it. Omega would be something that had to be supplied to the reader in this problem, because it's going to be a phasor domain problem. Now that means this value of I right here, and I'll put it here, I would be found as simply V, which is VL at an angle of 0 degrees, divided by this. All right, I'm dividing that by 1 over J omega C. You follow me? I'm just following the definition of current as voltage over impedance, correct, everyone? And can y'all hear me there in the back, everybody? Everybody got this and see it? All right, now if that's the case, y'all see here that if I take this 1 over J omega C, it's really going to be what? It would be J omega C times the voltage VL. Do you agree with that? And you'll notice the voltage I put at 0 degrees. Whatever that angle is, this angle is going to be 90 degrees ahead of it. Do you agree with me, everyone? Now, what is this in terms of an angle? If I have J, how can I replace J in terms of a magnitude and an angle? Anyone? It's a magnitude of 1, whoever said that's right, and it's an angle of 90 degrees. Do you agree, class? So I can rewrite this as simply omega times C times VL at 90 degrees. I'm using degrees, not radians. You follow me? Now, remember what the definition of conjugation is. Now I'm going to find the complex power associated with that capacitor. And that complex power is going to be V, which is VL, at 0 degrees, times I conjugate. Well, when I conjugate this, what do? I get omega times C times VL, only the angle will be minus 90 degrees. Do you all follow me on this? Right? I want you to take a careful look and make sure you understand why I've done what I've done. Because it's what? This is I, and the complex power is equal to V times I conjugate, right? So I found I have to conjugate it, change the angle, and now when I get complex power, I have this times this, and what do you see that's becoming? Isn't that just what? Omega times C times the voltage across that capacitor squared, the magnitude, and it's at minus 90 degrees. Do you all agree with me there? You're not liking this, you're not seeing how I'm going to use this yet, but you're about to. You all with me? Now, when I draw this, normally the way you do this is you're going to put this is kind of complex power plane, or the S plane. This is going to be complex power. Here, this is the real axis, and this will be the imaginary axis, or the J axis. All right, now just listen. What I've shown you is this. For that capacitor, I simply have this. I have J omega C times VL squared at minus 90 degrees. Well, that's plus 90. That's minus J minus 90. So I simply have something down here at omega times C times VL squared. Don't I, class? Now I'm just showing you right now in the complex plane where I have a real and imaginary axis, how this would be represented. That's just for the capacitor. Are you with me? Now hear me now. If I go ahead and I put a normal load on here, and I'm about to, and just listen, I'm going to put a load here, And this load is going to be something that's got a normal positive reactance and inductance in there. So I'm going to say this has got a value in terms of impedance, and I'll just use Z here. Thank you. I'll call this Z load right here, and I'll say that Z load is just equal to, say, 10 at an angle of 30 degrees. Now that plus 30 degrees tells me that there's an inductance. It's got some resistance in series with some inductance. You with me? That 30 degrees just gives me that. I don't need to know the value of the inductor or the resistor, just the magnitude and the phase angle. You with me? Now let's get the complex power associated with this load right here. That's the load. On purpose, I chose a number there. So I'm going to come down right here, and I hope you appreciate I'm trying to make sure that I keep this in view right here. So when I take a look at the complex power associated with this, and I'll just call it P load, or I'm not P, but S load right here, then I can say that that S load, now just watch, right here, would be equal to V. Well, the voltage is VL at 0 degrees, right? And then I need I conjugate. Now, what is the I going down here? Think about it. Oh, I'm sorry, thank you. This I would be what? It would be this voltage, in other words, this I right here would be equal, and that'd be I load, equal to VL at an angle of 0 degrees divided by what? 10 at 30 degrees, right? Y'all follow me? That's the definition of that current going through the load, right? Voltage divided by the impedance. I created an impedance out of thin air, just for this example. So that's going to be what in terms of I? That's VL over 10 in terms of the magnitude, right? And the angle would be what? Minus 30 degrees. Agreed? This is important. So the current would be lagging the voltage, as you've seen in most of your homework. Correct, class? Now, with that in mind, when I go ahead and calculate the actual complex power associated with this load that I created, it would be that voltage times this conjugated. You see how the angle becomes a positive 30, right? So it would be VL here, then it would be divided by 10. I just chose that number, and it's at an angle which would be what? When I conjugate this, I get a plus 30, don't I, class? So it's going to be plus 30 degrees, and that means my S load here would be equal to, in this case, it's VL squared, that's in magnitude, divided by 10, and it's at an angle of 30 degrees. Do you all see that? This is real important that you see what I've done and why I've done it. Can't hear you. Okay, is everybody okay with that? And keep me, please, if you see that you cannot see, let me know as soon as possible. I'm looking over there, and I think sometimes I don't look over there enough. I'm looking here too, but honestly, I think my eyes are more focused on that. All right, now I'm going to plot this. Are you with me? Where does that? That's going to have a magnitude of VL squared over 10, right? But it's at an angle of 30 degrees. Now look, that means this angle is 30 degrees, and this is VL squared divided by 10. Are you with me, everyone? Now hear me now. If I wanted to, I could take this and take a projection down here and find the real power, right? That would be VL squared over 10 times the cosine of 30. That would be the real power here. That power on the load would be equal to VL squared over 10 times cosine of 30 degrees. And it's a little messy there, but you follow me. This would be the reactive power, and that would be a value of J, and it would be, the symbol is Q, and that would be J times VL squared over 10 times the sine of 30 degrees. Y'all with me? Now please hear me here. Are you with me, everyone? Now I've shown you complex power for this load and this capacitor, both in the same circuit. They're in parallel with each other. The sum of those two complex powers is the complex power used by the system and supplied by the source. You follow me, everyone? I want you to get your head around this. Make sure you see what I'm doing and why. Got two complex powers, one of the capacitor that's strictly minus J, One complex power associated with a load, a fictitious load, but an inductive load. I plotted them. The sum of these things equals the total complex power. Do you all hear me? Now, when I draw the final, this is, by the way, called a power triangle. If you ever hear that term, that's what they mean. They show reactive and they show real power drawn like this for any system. How many are mechanical engineers in here or aerospace engineers? You will be using something like that for your systems that are electromechanical systems. Has anybody used this before? Any mechanical engineers, especially? Not. Have you had a course in electromechanical machinery at all or not? Has anybody? Don't you get one? Or it's not mandatory? Okay. I'll talk to Dr. Birch about that. I was under the impression you did. Maybe that's a graduate course. Anyway, now the sum of these things is the complex power in the system. There's one thing some of you picked out right away. It looks like this capacitor is canceling the imaginary or the reactive power, and that's exactly the goal. So when I take a look at this, when I take a look at a power triangle where I just get the net real and net imaginary, the real power will never change. The real power here will be equal to VL squared over 10 times the cosine. In my case, it's going to be the cosine of 30 degrees. Only the real load burns real power, not the capacitor. But now the imaginary power, we don't know if it's plus or minus. We know whatever it's going to be, it'll have a component of J, and then it will have this value, which is VL squared over 10 times the sine of 30 degrees here. But it would be minus omega squared C VL squared, right? That's this reactive power, which is omega times C times VL squared. Now, you can see this would be the new power triangle. I'm going to say one thing. This 30 degrees would be referred to as theta old, and this new angle, whatever it is, this right here would be theta new. Now, this isn't coming together quite the way I want, but I'll get the information out. When I looked at this, before I added the capacitor, if I wanted to know what the power factor of this load was, now hear me, I didn't say this prior. Once I have the complex power, if I just take the cosine of the angle, when you plot them right there, that is the power factor. Do y'all hear me? Now, it's implied that you already know that because you're going to have the current and take the conjugate of the current and multiply it by the voltage. But this is the original power factor, the cosine of 30 degrees, which is what, 0.866, something like that? And if we adjust this capacitor right, if we make this to have a net value of 0, then we would have strictly real power, no reactive power. Do you follow me on that? How many do? All right. If, in fact, we allow that capacitor, remember, this is subtracting from this. If we allow that capacitive reactance, or I should say the omega C VL squared to be equal to VL squared over 10 sine of 30, then we would have 0 reactive power. You follow me on that, class? I'm going to give you more information. That's the goal of industrial engineers when you are running a power plant. You would like, at all times, the reactive power to go to 0, which means the power factor would be 1. You've done power factor problems in industrial engineering, right? I know you have. I see your heads bobbing there. Yeah, that's the goal. That's really what happens when you put a capacitor in parallel with a power plant. Now, the truth is you're going to have variable or adjustable capacitors that will have a variation in values. Usually they don't, it's not a knob you turn. It's simply a computer-driven thing where it will automatically find out what the power factor is and then either add capacitance or remove capacitance to get the power factor as close to 1 as possible. You follow me on that, class? That's what really goes on. If you do it on the cheap, and I've not been out to a major textile plant in a very, very long time, but what they would do is have some guy, a foreman or something like that, that would be putting capacitors in parallel or taking them out based on a reading of the power meter. I don't know if they even show that anymore in your classes. Have you seen anything with a textile mill in the old days? Anything at all? Nothing. All right, well, you ask your teacher, he'll tell you or she'll tell you about it. Now, let me say, I try to do that with a lot of emphasis on real values here. I'm going to just make one simple thing. Remember, that power factor does not have to be zero. I mean, excuse me, it doesn't have to be 1. It could be reduced to a certain amount. You with me? So you could calculate some value of capacitance that would reduce it. I'm going to give you some problems on that, and I'm very, very aware that this class gets nervous about these quizzes and stuff like this. This is not a hard quiz, but no matter what I say, it seems people try to make it into the most bizarre problem in the world. Please don't do that. Realize the quiz itself is not going to be hard. I'm going to put out more information about this and ask you to do problems. On Wednesday, we're going to go over more. There's likely going to be a quiz this Friday. I'd advise you to keep up with this because we're going to do 3-phase on Wednesday, no matter what. Okay? We'll do the quiz now. Everything off your desk, and I will move people around as usual. What? Yeah, here, you can sign. What? Not this one, next one. Yes, yes. Does anybody have an extra calculator that they don't mind lending to someone just for me? Class, when it says power factor, it's the power factor at the source, not the load. I give you the power factor at the load. Everybody got that? Don't just write down.